Can we see the participants over here?
Yes.
Okay.
So, Hong, you can start now.
Yes. So welcome everyone to join this webinar series. So my name is Hongjian San, a professor in the engineering department at Durham University. So today I'm going to chair this webinar. So as you know that our webinar series run a few times already. So the webinar series is designed to bring together expert innovators from both AI, but also sustainability domains together. So with an overarching goal to accelerate progress towards AI and also its use, so the series aim to engage, inform our communities about the groundbreaking research we have done, developments we have been involved, and particularly focus on intersection between AI and sustainability. The webinar series will also cover a range of applications about AI and how we use them to improve net zero progress. Particularly, we will focus on achieving net zero target by thinking about energy, transport, environment, agriculture, and food system. So today we have our speaker, Professor Danny Williamson. So a brief introduction about Danny. So Danny is a professor of data science and AI at the Land, Environment, Economics and Policy Institute at the University of Exeter. And he is a principal investigator of Add Trees project. As you know, Add Tree has received funding from EPSRC for about 1.7 million, sponsoring a number of researchers in the consortium. So Danny has made a significant contribution to several key areas of statistics, particularly uncertainty quantification using Gaussian processes, and also calibration of environmental models, and particularly around the use of AI as well. He obtained his PhD in statistics at Durham University in 2010, then took a postdoc position at Durham as well, and then joined mathematics department at the University of Exeter in 2013. In that time, he has held EPSRC and also Alan Turing Institute fellowship and won the Lindeline Prize for his paper on belief ownership in complex statistical models. He moved to economics now in starting from 2023. So today he will present Add Tree, digital twins, and decision support for net zero and uncertainty for about 35 minutes. So after that, we will have about 15 minutes for Q&A session. So by the end, we will have our closing remarks and announcement for next sessions. So now, without any further ado, so let's welcome Danny to present his work. Thank you.
Thanks, Hongjian, and thank you very much for the warm introduction. So I'll begin. I am Danny Williamson, and I'm very lucky to lead this project. So Add Trees, definitely the name Add Trees came first, as you'll see during the slides. The actual title we hammered into the acronym, but it does what it says on the tin. So decision support, digital twins, and the restoration and enhancement of ecosystem services is what we're interested in. And I'm very lucky to lead a very diverse team, diverse particularly in subject area, so from data scientists and statisticians through economists, ecologists, geographers, really trying to pin down all the facets of this type of problem. So we also work with all of these partners, and we work quite closely with them. We run workshops with them, and they're helping us design our decision support tools. Particularly Forestry England and the Army have been very engaged, and we've had several days working with them to get what they want out of these things. Because after all, the people that will deliver net zero, a lot of them own land, and these people own a lot of the land in the UK. Okay, so the UK and net zero, I think we all know that we must hit net zero by 2050, but it is law. It's not just a goal. It's part of the Environment Act. And that's not going to be just achieved by cutting emissions, but we're also going to need some carbon capture technology. And I think we need a portfolio. Now, my actual opinion, I think, is that it's only possible to really deliver what we need with a sort of large-scale carbon capture and storage. But I think that's also far enough away that all of the other technologies are essential as kind of like a bridging loan to coming online of major CCS. The government, or at least the previous government, seemed to agree, because also in UK law, we must plant another 500,000 hectares of woodland by 2050. So the big question is, well, where should that go and how are we going to get it there? On the right here is a screenshot from one of our apps, and we'll show a movie from this in a minute. But it's worth introducing what these things are. So this is the smallest discretization of land that the UK kind of recognizes. These little, they're not squares, these are regular polygons, let's say, are called land parcels or field parcels. So they're roughly fields. And the colors come from CEH's land cover map. So light green here is grassland or livestock farming, right? So grazing land. The bright yellow in the land is arable farming, so crops under some sort of rotation. The orange is like a calcated grass. So this is an area near Branscombe on the South Devon coast, not far from where I live, and we regularly go to the beach here, and you can walk along the cliff tops on that calcated grass. The dark green, by the way, is trees, and there are a bunch of other colors, water and bogs and so forth, that we don't need to worry about right now. So if we could just plant trees on this land, the decision is really which of these field parcels should we change into woodland? So where should we do that? What species should we plant if we decide to convert a land parcel to woodland? When? Because there are something like 2.5 million land parcels in the UK, and there aren't that many trees. I mean, there's probably 2.5 million we could plant, but you're planting enough to cover each parcel, let's say, in a woodland. And then the snag is that we can't just decide to plant on all of these parcels. Most of the land is privately owned by someone. Now, some of the largest landholders, like the Ministry of Defence, work with us already, so they could decide where to plant trees. But most land is owned by farmers. So if we're working with DEFRA or someone like that, we have to work out how can we incentivize those that own the land to change land use to planting trees, for example, in the right way and at the right time and using the right species. Okay, so changing land use doesn't affect just trees. If you replace farming with trees, you remove some food production and impact food security. And if that food production reduction causes you to need to import food, it might not, you might be exporting it, but if it causes you to import food and that food is produced using less efficient from a carbon point of view technologies, then you may have actually leaked CO2 into the atmosphere, even though you planted trees. Of course, you're going to store some carbon, so you're going to help towards net zero, but that's not the only thing you've done. You're going to impact farm incomes. Hopefully, they would only plant trees if that would help them, but there's some uncertainty there. We're going to impact biodiversity. We're going to change water quality, mostly by removing fertilizer runoff into the water, but trees also have some impact, and the quantity available. There'll be impacts on flood risk that might be away from the parcels you're considering. There'll certainly be fire risks if we're planting trees. And woodland can generally be beneficial for recreation and health if it's near enough to populated areas. So when you're trying to solve this problem, where should we plant trees and when, you can't just consider carbon. And so what we've done brings models from many disciplines all together. So our modeling framework allows the user to consider planting on land that changes land use. And then we use several data sets, including high resolution climate and soil, and supercomputer simulations for trees and soil. Pest and disease modeling is in there. We have biodiversity models. We have a complicated model for farm production based on the Wofost crop simulator. We have flood modeling. There's a model for carbon exports if you change food. And all of these things lead to some outcomes. So the green ones are kind of ecosystem services, greenhouse gas removal, biodiversity, and so forth. We also have an uptake model. So if a policymaker is looking at this, they might pay people to change land. And then we have an agent-based simulation for who changes land, and then that impacts across the network as well. So if you're a policymaker making a decision here, or you own your own land making a decision here, whatever you do changes land use in some way that impacts across all of these ecosystem services. You might care about some or all of them, or only one of them. But in order to change this, you kind of have to simulate from all of these models to find out the answers. And at least our trees and soils run on supercomputers. And the farm production model is probably going that way as well as our climate resolution gets higher. Now, I'll come back to how we deal with that complexity in a minute. I want to show you the first thing that we developed on Add Trees. This app is complete, and this is kind of our digital twin order form. And it allows a user to define for us what is the area of interest in terms of where can you plant and what can you do on the land. And also which of those outcomes we just saw, GHGs, fire risk, and so forth, do you actually care about? So on the first page of the app, and I'll start the movie now, you can play in a Google Maps type environment and search around the UK and define your area of interest. You can also upload a shapefile, which is nice and neat. Here I'm zooming into the area north of Exeter where the university is. There we are in this little patch over here. And I'm now able to select land parcels. So all of these parcels are clickable individually if I want to. And I've got a lasso select and a box select. And I can pick up a bunch of parcels. And when I've selected them, they appear according to that CEH color key that I talked about before. And I'm selecting an area as if this is the area I'm considering as my area of interest. And I might be planting trees on some of this area, or trying to consider where I should plant them here. So maybe I own this land, for example, and I want to work out what to do with it. So having played with that page and defined your area of interest, this will form the sort of screen that you see when your digital twin opens, and it will allow you to choose what you plant and when and so forth. In the next screen of this generator, you then say what you can do on the land. Now, one of the first things I always do is find all the urban areas and the bogs and the other places where we could never plant trees and make sure that we can't plant trees on them. So here I'm doing that, selecting all the non-plantable areas, and then I hit the maintain current land use, and those go out of consideration. And then having unselected all of those, I can then decide what am I allowed to do on this land. Now, to make it easier, I'm just going to define one thing. I'm going to have, I can add trees in every parcel is going to be the idea. So I give it that name. And the activities I'm adding here are, I'm going to create some woodland. It has some properties. And then I'm going to say what types of trees. Right now, we don't have individual species, but that's part of the project. And when I've done that, I'm just going to pause the video for a second. That has defined on all of these parcels, I can plant trees of the type that I described. There are lots of other things that you can add. You can do agroforestry and habitat rewilding and all sorts of other things too, but we'll just look at a woodland example for now. Where's my pointer gone? There it is. How do I restart the movie? Sorry, we can't restart the movie. Let's go. There we go. Now it's starting again. Note to self, don't pause the movie. Okay, after that, you define the outcomes you're interested in. So here you can choose from all those ecosystem services we saw in the big network. So I'm choosing carbon and I'm making a specific definition of what I care about. Do I care about a 2050 total or some particular target? And then I can add from a whole set of other outcomes. Maybe I'm interested in recreation. Biodiversity has lots of different things I can add. So I'm going to look at some priority species. I'm going to look at some pollinators. And there's the greatest of all time moth that I'm going to add as well. Maybe it's probability of appearance. And when I finished adding all the things I care about, I hit export. And these 3 files in the top corner are sent to Add Trees. and then a decision support tool based on a digital twin is automatically generated using some of the technologies you're about to see. And we'll come back right at the end in the last slide to show a movie of what that decision support tool looks like at the moment. And we'll come back to that later. Okay, so all of that is defining a subnetwork of that big network I showed before. And from that subnetwork, I'm going to define something called a digital twin. I know there are many definitions for that, so I'm just going to give you mine, and we can see how we like it. So a digital twin is going to be a vector valued function. So as in you run the function and you get lots of different values. So for that last digital twin, we'd get carbon, we'd get recreation, we'd get some biodiversity metrics. It's a function of decisions that you can make, some inputs that you have. So the decisions are maybe where do you plant, or for a policymaker, how much would you pay a farmer to change land use? The X's here are forcing inputs, so climate, soil, topography, things that are going to happen or have happened if that's important. And the thetas are some model parameters that we will learn with data kind of online as it comes in. Now, the vector valued function isn't simple. It's actually a composition of individual models from different disciplines. So we have people from different disciplines develop biodiversity models than those that develop tree growth models, than those that develop agent-based models for farmer changing behavior, right? So you have to compose these models together. And so you can do that and you can satisfy yourself that this notation works. And what it does is it makes the forcing inputs contain outputs from other models in the network. And that sort of defines what's going on here. So if you want to work out what would happen if I change my decision, somehow you've got to evaluate this function, which is a composition of a bunch of other functions, all of which, or some of which at least, are expensive. Okay, so function composition can get messy. Here's my canonical example. So suppose we take this nice smooth cosine wave here. It's got some inputs, and then you get a nice smooth function at the output. And we take the output of that and we put it as the input of this next function, which has got sort of a bump, but it's still fairly smooth. And we take the output of that function and we make it the input to this function, which is kind of something that's periodic, whose period is sort of slowly flattening out. What we get, even in one dimension, is this sort of really horrible, spiky, non-stationary, nonlinear function that for most traditional methods within AI for building surrogates is kind of hard without getting loads of simulations of it. And we'll come back to this idea that we are composing complicated functions from simple ones, but at least the point here is that the output of any digital twin as a function of the decisions, if it's composed of even simple functions, could be messy and horrible and nonlinear. Particularly, these functions are going to live in a lot more dimensions. Now, my research has always used Gaussian processes and lately deep Gaussian processes to build surrogates of expensive functions. There are lots of ways of building surrogates, a lot of them with neural networks, or there are other methods too. I've always come back to the Gaussian process because it gives you uncertainty quantification. So for any particular point in the input space, I get a distribution of the output. And that uncertainty can be calibrated, and then you can use that uncertainty in forward calculations, particularly when you're doing decision support and you want to communicate risk. I find that uncertainty to be necessary. So that's why I use Gaussian processes. And lately, a few things have happened in Gaussian process land that make them kind of attractive again. So the first is that deep Gaussian processes kind of look a lot like neural networks. So you go from input to output, but instead of just a Gaussian process, which is a sort of functional representation of a multivariate normal, you have Gaussian processes at every node, and you have lots of hidden layers that you somehow infer. So it's like a neural network in that here in a neural network, you'd have some input. It would be a linear combination of all the inputs and then a nonlinear transfer function. and you go through like that. And instead with the Gaussian process, here you have an uncertain function, and here you have an uncertain function of the hidden layers and so on. And it turns out we can impute those things quite well. And when you fit a DGP to something, it can learn even these horrible types of functions if you give it enough simulations. Here we give it 100, and it's doing a pretty good job. One of the problems with Gaussian processes, particularly if you're going to use those for digital twins, is the curse of n cubed. So GPs don't scale well, and deep GPs are worse. And that's because when you invert the covariance matrix that you need in order to do inference, that's an n cubed problem. So as the number of runs gets larger, both the speed and the memory required goes up in n cubed, and eventually your computer will fall down. And we've had so many masters projects here where we've sort of got people to compare all kinds of neural networks with Gaussian processes. And the idea is, for low numbers of simulations, Gaussian processes win, 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 then they break, and neural networks are the only thing that can do it, and then they win. What we've been looking at since about 2018 are these variational inference ideas where you kind of avoid the need for this inversion problem and do some other tricks. But that stuff doesn't really work. It doesn't estimate the tails very well. So here's a variational inference DGP for the step function, and it always misses off the tails. And there's countless examples of this in literature. Whereas the full inference sort of has this interesting uncertainty that you need if you're looking at tail risk and that sort of thing. A recent discovery called the Vecchia approximation. Well, the Vecchia approximation isn't recent. That's many years old, but its application to GPs was only discovered a couple of years ago. And something we've done over the spring of this project is to put it into all of our software, and suddenly it means scalability looks possible. So let me show you what it looks like. So Vecchia approximation starts with the premise that there are n factorial factorizations of a likelihood in any problem, right? So if this is a joint distribution of your data, then you can factorize it in n factorial different ways. They're all valid. That's fine. So Vecchia approximation picks one of them, and which one may be important. There are methods for that. And then what you do is, instead of, for all of these ones where you're conditioning on large amounts of data, you limit the number it can condition on. So maybe to 10. In our software, it defaults to 25. You could pick 2. And that basically thins out this thing and provides an approximation to the joint likelihood. Now, what Katzfuss and Guinness and those guys figured out a few years ago was that for Gaussian processes, and therefore for deep Gaussian processes, this Vecchia approximation induces sparsity in the precision matrix, which means that for deep GPs, if you apply this approximation, you get Inler-like or Laplace approximation-like speed, even though you're doing kind of full Bayes inference to some approximation. So here's a sort of study that I knocked up this week. Unfortunately, I chose this Levy function, which is admittedly horrible to emulate, but it is stationary. So it means GPs will outperform deep GPs. The plots here are for normalized root mean squared error. So low is good, and time taken in seconds, and the scales are log. And you'll see with the deep GP and the Gaussian process that those curves end because the code falls down, and that's on a 120 gig RAM machine, or 128, I think. Whereas the Vecchia approximation, even on these scales, it goes and you can do kind of 20,000 points in 20 minutes for a deep process, which I think even last year I just thought was always going to be impossible. So suddenly we feel like we can start to compete in terms of scalability with neural networks. And that makes what I'm about to say even more attractive for me. Okay, before I get to that, let me show you a basic application of emulators, deep GP ones at least, for tree growth. So this is our emulator inside an app for the tree growth model Jules. Jules is the UK simulator for land cover. And when we press the Add Trees button, because we couldn't resist having an Add Trees button in the app somewhere, you get a prediction of the carbon that would be stored by 2024, so 0 at all of these locations, about 4,000. We can only run joules on a supercomputer, and we'll only ever get about 100 simulations a go. So doing this is quite good anyway. But we're able to predict for all of the cells in the country. This is a 1 kilometer resolution example for various reasons. It's all clickable, and once you've clicked it, you see that you get a prediction of the mean and the uncertainty everywhere. And it's nice because you can see features coming out of the model, even with a very sparse training set, such as planting conifers in the southeast under extreme climate change. This is RCP 8.5, means that they don't like it. They kind of suffer with the rich soil, and the extreme climate means the trees just don't grow. That's all great and everything, but the error bars are kind of large in places. And something that we cracked in November is this idea of using linked GPs, which give you analytic updates on these propagations of different GPs. I'm going to say more about that in a second. We've worked out how to use these for these net zero problems. So let me give you a bit of background. About 10 years ago, no, it was 2016, so 8 years ago, I was at a conference in Lausanne when Ksenia, I think her first name is, presented their linked Gaussian process idea. And what they showed for the first time was that if you have inputs and 2 models and then some outputs, you get better uncertainty quantification if you emulate the individual models and then use these analytic recursion formula than if you take the input of the system and the output of the system and fit a single GP. Now that might seem obvious now, but in the room, the discussion session went on for half an hour. Nobody could believe it. And I have to admit to being skeptical myself. We now understand it works so well because you actually get the data from the internal layers of the coupled process. And that data also helps you learn the global function. Now, we realized that a network like the one I showed at the start is actually just like a deep Gaussian process, except when you're observing the runs of joules, you've got some exposure of some of the hidden layers. And we realized that, well, if a deep GP is like a linked GP, and we get some partial of the exposure of the hidden layers, then perhaps we can jointly infer any network of models with one single deep Gaussian process. So we called that linked deep GPs, and we published the paper on arXiv. And we've since worked out how to use that to emulate interesting models like joules. So I'm going to show you an excerpt from the AdTrees movie, which is linked at the end. And it starts by showing you how deep Gaussian processes work. So there's just a collection of these individual Gaussian processes all linked together. That's a deep one. And then it shows you how they can train to learn things faster than GPs. So if that's a function and we use all of the points, we get a low error. And then you start adding points at random or using some intelligent active learning algorithm, and you can quickly get the error down with a very partial sample with a deep Gaussian process, as long as you do this structural optimizing step, which we have in most of our packages. Now, what we figured out was that if we have a lot of expensive models, the way you can do it is by fitting deep GPs to all of them, like this. Then they learn the network. It takes a while. And then we have a linked deep Gaussian process that quickly predicts everything using the information from the hidden but unmasked layers. So in the middle is what we showed before, and on the right is the new thing that knows those internal nodes, those internal functions. And it quickly locks the answer in a fraction of the number of simulations that you would need even to learn the deep GP to the same level of accuracy. So we've started using them in sort of innovative ways, even to emulate single models. So Jules takes weather and soil as an input. It takes 30 minutes on Jasmine, and it gives you this curve. We know that different processes are going on for trees in different months. So instead, we build DGPs for the single month processes. So you've got growing and various other things that trees are doing. We learn each of the single month transitions of tree growth. And once it's finished, we link them all together to provide a surrogate that actually grows trees with uncertainty. And what you'll see when it happens is the uncertainty is remarkably small. And that's partly a property of Jules, but it's something that means that we can do this better than I even thought we would be able to when the project started. Okay, so that's some of the things that we've been inventing on work package 1, which is a sort of technical AI part. And the second work package, we've been working on downscaling climate to parcel level, because our apps are really trying to allow users to figure out what to do on individual fields. And climate does change from field to field, particularly when you have hills and valleys and so forth on your land. And researchers on the project have developed the Mesoclim R package. It's linked in the references. And what this does is it starts from UK CP18. For those of you familiar with Chesscape, some of the apps you've seen already have used Chesscape. We're now moving away from it for various reasons. One of which is it's not so good at, well, we don't like its pattern scaling elements. So we're moving away anyway. The other is that it seems to not make sense to downscale a 1 kilometer downscaling. So we'd rather go back to the original model simulations at 12 kilometers. You combine those with sea surface temperature data and a lot of physical knowledge that's based on the project. And what we have is a package that gives you all the outputs you need. It actually gives you distributions of those to run the models. So Joules and Wofost and other things that require climate. So they need min and max temperatures, and they need wind speeds and directions, and they need precipitations and so forth. And you can see this is an area in Cornwall called the Lizard, that the change at parcel level is actually quite stark, and it's quite interesting. It's based on the topography of the land, I guess. Data is really important for digital twins. So our stuff means we can emulate that whole network or any subnetwork of it. But we are going to need to integrate data from each individual land parcel. So when we have farms, we're going to have data. And there are 3 different ways to bring in data. One is to just substitute parts of the network with data if you have it. We don't tend to do that, although climate data, I suppose, is a forcing variable. And the other ways are to either estimate parameters in the model when they're static, or to estimate initial states. So suppose we have different soil variables that have soil moisture and nutrient content when we're simulating crop growth. You might want to use data assimilation to estimate those. In Add Trees, we have some remote sensing. So we have leaf area index for every parcel. We have some stuff from the Woodland Carbon Code to calibrate tree species. And then we have some data from DEFRA on yields from different crops on different parcels for about 6,000 parcels a year since 2016, and management in terms of amounts of fertilizer used and when it was applied and so on for about 3,000 parcels for 20 years. So all of that data has to come in to learn a lot of our models and to give us, if we're going to plant trees, gives the soil the right initial conditions for doing that. And then our last work package, so that the calibration is work package 3. Our last one is decision support. So once you can build a surrogate of a network, and you can build a surrogate for any network, then the types of decision support you have are some scenario analysis. So choose a few decisions and present what the all of the outcomes are, or a distribution of the outcomes. That's fine. A more machine learning approach is to sort of optimize, so find the best decision, the one that, say, maximizes some utility function, or to show a Pareto front, like a multi-objective optimization. So here are the trade-offs in carbon and biodiversity. And My own view is that that's not a good idea, because users only ever want to share some of the things that they care about. So when we work with the army, they're working with us because they have carbon targets and they want to meet them, and they do care about other things too. There are things that they care about that they won't share with us, like having a certain portfolio of training environments and what that portfolio should look like, about being able to test weapons and so on certain types of land. We'll never know what any of that is, and nor should we. The point is, it really factors into their decisions, so optimization might be slightly misguided. So instead, we'd like to provide the kind of decision support with these digital twins that allows users to explore all the options that work with the targets they're willing to share with us. Okay, so suppose you have a bunch of targets, like a carbon target or a biodiversity target, then we would try to find the set of all decisions such that the probability of meeting those targets is bigger than some threshold, maybe really, really high. And we have a way of finding that set, and we're working on some algorithms to sort of explore that space. And I'm going to show you a couple of things from apps that we've created, and there are 2 1-minute videos in those apps, and then I'm done. So the first is an app that we've been developing on a project, a sister project, Net Zero Plus, but that I'm involved. I lead the AI on that, and it includes some of our researchers too. And it shows the idea quite neatly. So here, this is an app for DEFRA, so they can change the price they might pay for managed coniferous trees or managed deciduous. Managed mean you thin every so often and you use the wood for timber. You can have some unmanaged woodland. My pointer keeps going in and out of view. I don't know why that is. Sorry about that. And you can have a price per ton of sequestered GHGs, and you have an annual budget. And as the movie starts, the user can move those along and see what the planting input would be, or what the planting change would be, for different combinations of these budgets and prices. And you can see up the top left, it says targets not met. And here we have some targets on biodiversity at the bottom. So we want to increase these groups by 30%. And the red zones here indicate areas of this space where you're more likely to find target compatible strategies. So the users can move towards the redder zones and find policies that meet the targets. Now this one plants lots of deciduous in the southeast, but we can also, once we can find the space, we can cluster inside it and we can show different thematic types of things. So in this one, this other target compatible strategy, when you look at the maps, it plants conifers everywhere, and it has the impact of kind of maximizing greenhouse gas reduction, but you don't get as much diversity in species. So that's the kind of thing you could do if you're thinking about trying to show the whole space of decisions. And then the final picture is the app that we ordered in that first video. So this is the north of Exeter and all of those cells. You can see here on the right-hand side, there are sliders for all of those ecosystem services that were ordered. So there's carbon stored and the change in species richness, and the greatest of all time moth is in there, and also the area planted. And as I start the video, the user can move around with the sliders, changing the targets. And this first window will show you kind of an optimal map or an optimal planting strategy that still meets the targets. Now, as I move these, because I'm allowed to plant the whole area, everything's allowed. As soon as I reduce the area, it's going to say nothing's allowed, because I can't meet those targets by only planting on 3 kilometers or less. So if I start to reduce my targets, eventually I'll find a strategy that works. Here's one. And each of these parcels is clickable. So the user might want to click on one or more parcels and say, I definitely want to plant here because I already know that I do. So keep this one clickable, please. Oh, sorry, keep this one clicked. And then in the second page, once I've clicked some parcels, I can look at different strategies that still meet the targets, but are somehow far away from each other. So as I click the randomize button a bunch of times, it gives me different strategies, always keeping the red ones highlighted, that meet the targets. And right now our work package is working on different strategies to find this space quickly in app, because even if you have just 125 cells, there are trillions and trillions of possible combinations of planting, and also clever ways to show diverse yet interesting strategies that meet the targets. That's all from me. There are a bunch of references here. The AdTrees movies are fun watch. All of our software is on CRAN or Conda, and the Vecchia approximation is in beta, so you can get that from our GitHub page. And the last GitHub page has the parcel level downscaling, which is working, but is still also under development. Thank you very much.
Thank you so much, Danny. Thank you. Very excellent talk. Thank you. So now we have Q&A session. So if you have any questions, would you please post that in the comments area? So before we see some questions from our audience, I have a couple of them. Okay, so you mentioned about tree species. So have you considered, how they have impact on your model?
Yeah, so one of the big pieces of work that the postdocs on one of the work packages is undertaking now is the calibration of joules to different species. And what data we use for that calibration is a bit complicated, but the idea is that there are parameters inside the model that define how the trees behave. And currently in joules, there's only deciduous and coniferous trees, but the woodland carbon code has lots and lots of different species and different yield curves. So what we're trying to do is actually find the values of those parameters that actually look enough like the woodland carbon code curves under historical and then run those forward. So we're currently trying to calibrate tree species in joules as part of the project. Now, once they go in, you're not just planting or not planting on a particular cell, but you get to choose which species. So the combinatorics gets harder and harder and therefore more interesting.
Yeah. Thank you, indeed. So you also mentioned about the parcel or cell size. I mean, I'm not quite sure how this will contribute to your model. So if you downscale that to be meter unit, probably it's very hard because your n dimension is going to be huge in that case.
So we downscale to parcel level, which is up to a few tens of meters. But the trick is not to try to downscale the whole country, right? Because that would be, as you say, I would say not very hard. I would say we can't do that.
Okay.
But a user usually only cares about some finite area of land. So the idea is to downscale to order for those individual users, just for those parcels where we need it. And when we have something larger, so if we're doing one of those apps for DEFRA where they can change policy, to have kind of emulated some regions with downscaled climates, because there is no ambition to do a parcel level UK downscaling and provide that data set to the community. That's not the career I want to have.
Thank you, Danny. All right, so let's wait for other comments or questions we have.
While we are waiting, I have a question about coupling models in general. And the coupling or the interface conditions is some topic which I've looked at a long time ago. And if I understand correctly, you are initially doing machine learning model for each component first. And that will have an approximation. Is there a way do you do projection to ensure that the coupling doesn't somehow reach conditions which is not realistic, that what you need to feed to the next model have to satisfy some specific constraints?
Yeah, that's a good question. We've been working on that exact problem. So there's an old paper. It's not old, but about 6 years old, called "How Deep Are Deep Gaussian Processes?" that in some sense shows that there's a limit to the depth of these things before it converges to noise. And it seems to us that that limit depends on the wiggliness of the functions, to the extent you can define wiggliness. I suppose you can. And wiggliness therefore means you get an uncertainty bloom with any machine learning method that isn't in the actual coupled system because of the reasons you've said, right? The sort of physical constraints limit those impacts. How you get around that, I don't know the answer if everything's super wiggly. I guess it's something to watch for, but when we've actually coupled models for real with these things, we haven't seen the uncertainty bloom with these technologies. They actually restrict the uncertainty quite well because you're using all the information from inside. And maybe that's saying that all the models we've used are not so wiggly in their output. I'm not sure. Because in all the test cases, when we work on the problem kind of hypothetically, it goes a lot less well than it does in practice because we keep giving it these like cosine functions that convolve with themselves n times, and then everything doesn't work so nicely. So yeah, it's still kind of a holy grail of UQ. I think the so-called uncertainty bloom, but I actually think it's not as bad in practice on lots of problems that we're seeing. But I guess in theory, those problems exist.
Thank you. There is a question here. Demetrius is asking, the model is trained on the network. It seems to me that the structure of the network would also affect the ability to represent complexity.
I'm not entirely sure what that means, but let's I'll answer a version of it, let's say. So the network here is a collection of state-of-the-art models from different disciplines that are meant to describe the ecosystem service impacts of some sort of land use change. And some of those models require inputs from other models in other disciplines. So if that's the network that you're talking about, then yes, the structure of the network is what it is, and you only need a sub-network of it depending on what a user cares about. And that network is as complex as it is. Now, if we're talking about the network of GPs that we use to describe that, then of course, how deep each one is and how we link them is the whole story for AI and how we learn that online. But in that case, the representation of complexity is sorted by validation, right? So if you can predict really well out of sample, you're obviously representing complexity well enough. And if you can't, then either you've under or overrepresented it, I guess. Don't know if that answered the question, but hopefully it was a good guess.
I have a tiny one as well. So I think somewhere you mentioned about sparsity issue. So can you elaborate that a bit more? What do you mean by sparsity issue in your model?
Yeah, so we're all familiar with trying to avoid inverting really large variance matrices. I think it's a well-known problem. Mm-hmm. And one of the best tricks for still having really large variance matrices that you invert is to work on the precision matrix and have that be sparse. So if the precision matrix is sparse, there are very, very good algorithms for you just use it. You don't even need to store the whole thing, right? And then like inner products have nice forms and Cholesky factors are easy to find and that sort of thing. The problem with Gaussian processes has always been that the covariance matrix is dense, and so the precision matrix is dense, and so you're in trouble. And if you know anything about Gauss-Markov random fields and those kinds of solutions, there are lots of models based on INLA that show that you can get sparse precision matrices under certain choices of, not of covariance function, but of restrictions on your model. But INLA's a difficult thing to work with sometimes. Vecchia approximation gives you that sparsity kind of for free. And it instead of, you can think of the algorithm almost like conditioning only on the nearest neighbors. I'm not saying that we do that, but it's a choice that you could make that would lead to a valid Vecchia approximation. And so that induces, you can see how that induces some sort of sparsity in calculation, but the fact that it gives you sparsity in the precision means all of the algorithms that have come in the 20 years for solving these systems with sparse precision matrices now come into play. And what I've always seen as the biggest drawback of the Gaussian process, that it can't scale because of the dense covariance matrix, seems to be answered. Now, how you do the Vecchia approximation is a career in itself, great, but it's exciting.
Thank you, Danny. Do we have more questions?
I haven't seen any questions. I would like to encourage everyone who's watching this afterwards to reach out to Danny and the team on the project website. Is that the correct URL, Danny?
Yes, I believe it is.
Yeah.
And the reference is in my talk with that. I'll try and make sure there's a link to the talk somewhere, if that's feasible. I'll have to check with some people that it is. But obviously, the YouTube video is here for all time. That's great. I guess it's the middle of August, right? So most people are in the sun, hopefully.
We're waiting for more questions.
So Danny, regarding the linked DGP, so do you think the different linking scenario could have impact as well? Because you generally mentioned that linkage between DGPs, they are useful, but how we link them, probably that have impact as well on the outcome.
Well, the linking, there's an analytic recursion for doing for finding the mean and variance of the overall process given the linking. So the decisions that you make are how many hidden layers are there? If it's really a model-to-model thing, do you have to do some sort of, and maybe Ahmed mentioned this, you have to do some sort of translation or projection. So if I have a model that requires like 10,000 inputs, say it needs a field, and my other model predicts that field, I'm not going to have 10,000 deep Gaussian processes and link them all in, because the thing will never ever compute. So I'm going to need some sort of low dimensional representation, and then I'm going to have to put the projection back onto that field in the model. So there are some decisions in those terms about how you do the linking. But once you've decided what the deep GPs are, the actual linking is an analytic recursion. Again, if you choose different covariance functions in your deep GPs, you get a different linking, because you're sort of integrating out all the previous layers, and their uncertainty depends on the covariance function. I know that sounds a bit dense, but there's actual details in the papers I put in the references on that. So.
Thank you, Danny. I think as we are running towards the end of the hour we have, so I would like to thank you again, Danny, for very excellent talk, very comprehensive. Thanks, I learned a lot. But also thanks for our audience who join us, sacrificing their valuable time, their summer time. It's nice weather outside. Thank you so much for everyone joining us. So regarding for more information, follow up. So Ahmed already shared information. I'm very also happy to announce that our next session is going to be on 20th August at 2 o'clock. So next session, we have 2 early career researchers to present their work. So they will be Oli Hardy from University of Lincoln and also Goyan Awangan from Northumbria University. So I'm going to copy and paste the talk information into our chat area. So welcome you all to join this session as well. All right, so that is the end of the webinar. Thank you so much again. Thank you. Enjoy the most of the day with nice weather. Thank you.
Thanks, Danny.